All right, let's summarize everything that we've talked about in this unit and do some problems. So when we standardize things, when we turn them and put them in terms of z, in terms of the standard normal model, that's going to move things around a little bit. So all of these normal distributions have the same shape. So standardizing is not going to change the shape, but it might change the center, right? Maybe I'm looking at, let's say this is 0 right here. Well, then maybe if this is our curve x, well, it's going to have to get moved over to become z, right? Because z has a mean of 0. So it can change the center, right? Because z, the standard normal curve, is centered, and it can also change the spread. Because if something has a big standard deviation means it's really spread out, right? This is big standard deviation, big sigma, as opposed to something with a small sigma would be like something like this. Small standard deviation. So when we standardize, when we put it in standard normal, that's making sigma equal to 1. So it could change the sigma. All right, so could have different means, could have different standard deviations, but they're still bell curves. It's just how wide is your bell? So a couple more summaries from this unit. The normal distribution is one that models continuous distribution of populations. It's a very, very common distribution for continuous variables. Again, like anything that has to do with life or nature, a ton of it is normally distributed. It's identified as a bell-shaped curve, kind of colloquially. Normal models are only appropriate for distributions that are symmetric and unimodal. All right, if they're not symmetric and not unimodal, we can't really talk about it being a normal distribution. We'll talk when we get into sampling distributions about, never mind. I don't want to get into it. Sampling distributions is the week after this one, and it's great, but a little confusing. Standard normal model, next thing on this little paragraph, standard normal model has a mean of 0 and a standard deviation of 1. We're standardizing it so that they all look like this really nice model right here. It just takes a couple steps and we get a really simple standardized model that we can use to compare things more easily. Again, it's hard to compare things that have different units. Wind speed in Chicago, rain in Portland. What's more rare? Let's standardize. That's one way of doing it. We write this as normally distributed. So that's what that n means, with mean 0 and standard deviation 1. That's how we write it. This is how you calculate your z-score. So in general, let's find some probabilities. Find that anytime you use z, right? Z right here, this means standard normal. Otherwise, we're going to use x. So it doesn't even have to tell us the distribution here. We know z means standard normal. So what's the probability that a standard normal random variable is less than or equal to 1.5? We can use GeoGebra. Less than or equal to 1.5. Standard normal, mean 0. Standard deviation 1. Less than or equal to 1.5 should look like this. 93.32%. And what this means, right? If a standard normal variable is less than or equal to 1.5, this means what's the probability that something is less than 1.5 standard deviations above the mean? That's what that means. So as soon as you see that z value, it has to do with standard deviations. So what's the probability that we're above, this is the next example, above 0.3 standard deviations below the mean, but below half a standard deviation above the mean? Well, again, you just use the interval notation in GeoGebra and say between negative 0.3 and positive 0.5, about 30.94%. All right, and that's all there is to it. Last thing, an incoming freshman took her college's placement exams in French and mathematics. In French, she scored an 82, and math, an 86. The overall results of the French exam had a mean of blah, blah, blah. Let's color code these. Let's have French be blue and math be red, because there's always a lot of red pens on math exams. All right. Anyway, French exam had a mean of 72, standard deviation of 8, whereas math had a mean of 68. It was lower with a standard deviation of 12. The lower mean, but higher standard deviation. Lower average on the exam, but more variation, more spread. Which one did she do better on? So you could just find the probabilities, or you can convert to standard normal. So we're comparing apples and apples. All right, so let's start with French. So let X be the score on the French test of a random person on the French test. So X is normally distributed with a mean of 82 points. And, oh, nope, that's not the mean. Mean of 72 points on that French exam and standard deviation of 8. And she scored 82. So she's more than one standard deviation above the mean. Whereas in math, right, let's let Y be the score of a random person on the math test. Then Y is also normally distributed with a mean of 68 points and a standard deviation of 12 points. And she scored 86. I'm missing an O there. Totally fixed. Fooled you guys. You can't even tell that there's a typo in that word, huh? So let's convert to standard normal. So the z-score is equal to her actual value minus the mean divided by the standard deviation. She scored 82. The mean was 72. Standard deviation is 8. Type that into a calculator. Should get 1.25. 10 over 8, 5/4. More than one standard deviation above the mean. Or 1 1/4 standard deviations above the mean. Whereas in math, we can do the same thing. And again, if you want to use x's, you can, but technically, our z-score here is in terms of y's because it's a different variable. Y minus y's mean divided by y's standard deviation. So she got an 86 on this one. So she got a higher score, but the standard deviation was a lot bigger. And the mean was 68, standard deviation is 12. Type that into a calculator. That's going to be 18 over 12. That's 1.5. So 1.5 standard deviations above the mean. So she did better on the math test, relatively speaking. Well, I guess even non-relatively speaking, an 86 is higher than an 82, but she did better on math. All right. Because this is more rare. Right? 1.5 standard deviations above the mean is better than 1 1/4 standard deviations above the mean. So 1.5 bigger than 1.25. So she did better on math. And that's how you calculate it. That's how you explain it. That's how you get the answer. And that is how you finish this unit. All right. Let me know if you have any questions. If you know what you call somebody from Wisconsin, I could probably Google it, but it's much more fun to ask you guys, see if any of you actually know it without Googling it. Or if it's something really weird, then maybe Google it and tell me anyway. Goodbye. Good luck. Have fun.